Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this 7th lecture of this mineralogy series, and in this lecture we will mostly learn about the phase diagram, mostly binary phase diagram and two component system. And in this lecture we will try to understand how this eutectic phase diagram is constructed, and when there is a kind of crystallization of melt is taking place, what kind of things will happen, and if we melt a rock, then what will happen. Okay. And in the previous lecture we were mostly discussing about the solid state this kind of reaction. So in that one we are trying to understand the polymorphism, and we try to understand that what are the different types of polymorphism. There is a displacive polymorphism, there is a reconstructive polymorphism, and there was a third type of polymorphism, that was order disorder polymorphism. And we try to understand that in the last lecture, that when we try to apply a larger energy and when we break the bonds inside the mineral, so basically when we apply pressure or temperature or both together, so our mineral changes its structure and it becomes a new arrangement of atoms and crystal structure, and because of that it has a completely new crystal structure. And when we have this kind of polymorphic reaction, we call that one as a reconstructive polymorphism. And if we apply a very little energy, and when the activation energy is very small, so what happens that when we release the pressure or temperature, the high temperature or high pressure phase can come back to the low temperature and low pressure phase, and in that case we have mostly a displacive polymorphism. And then we saw that we have a third type of polymorphism, that was the order disorder, and that is mostly dependent on the temperature, because at high temperature your atoms are vibrating more, and when the atoms are vibrating more, so it is very easy for a different atom to go to the different sites, and probability is almost equal. So we have seen the example of K feldspar, and in K feldspar at high temperature your aluminum can go to any of the 4 tetrahedral site, asymmetric tetrahedral site, but in the low temperature your aluminum will always go to the particular tetrahedral site, where next to that you have a potassium. So these are the some example of the polymorphic reactions. And there are another type of reaction, exsolution, that is also very important, and this happens after the formation of the rock and mineral. So this we will try to understand once we understand the phase diagrams little bit. Okay. So most of the phase diagrams is basically constructed. Most of the phase diagrams are constructed experimentally, and in this lecture we will mostly focus on the pure phase diagrams. Okay. And before that we try to understand that why when we mix two phases, so what exactly happen, our melting temperature will increase or decrease. So to understand that, what we should do, we should try to understand little bit about the thermodynamics. So little bit about the thermodynamics, and to understand that, what we will do, suppose if we have a dioxide solid, we have a dioxide solid and that is in equilibrium with a dioxide liquid. If we have this kind of situation, okay, when there is a equilibrium and your dioxide solid is in equilibrium with a dioxide liquid, so we can write down the equation in terms of Gibbs free energy. So our G of dioxide liquid will be equal to H dioxide liquid minus T S dioxide liquid plus R T ln X dioxide in liquid. We try to understand this term in the last lecture. So, if you have any confusion, you just go back to the previous lecture. So, you will understand the importance of or how we derive this equation. Okay. Similarly, we can write down the Gibbs free energy for dioxide in solid will be H minus dioxide, sorry, this one will be solid. Solid minus T S dioxide in solid plus R T ln X dioxide in solid. So, suppose if you try to draw the temperature versus free energy, this diagram. So, your dioxide solid will have a negative slope because it is free energy is a function of minus T s, and similarly you can draw the dioxide in liquid phase will have a higher energy at particular temperature, okay, and this is the dioxide liquid slope. So, dioxide liquid slope will have always a steeper slope compared to dioxide solid slope, because the at higher temperature entropy is higher. So, definitely when entropy is higher, so your G will be lower, okay, because this is a negative relation. So, basically at this point, when there is a dioxide solid curve is intersecting with dioxide liquid curve, that is your melting temperature, where your delta G will be 0. Okay. So, if we write down the delta G of this particular function, if it is 0, so we can write down this in terms of delta H m minus T delta S m plus R T ln X dioxide in liquid divided by X dioxide in solid. So, we can write down this equation like this, okay. And if we put this term this way, so if we can also rewrite this equation like R T L n X dioxide liquid divided by X dioxide in solid is equal to, I take a minus term and I put the whole term in the right hand side. Okay. So, delta H m minus T delta S m. Okay. We can write down like this equation, and suppose at equilibrium at this T m temperature, where your delta G is also 0. So, if we take at melting temperature, where this is equal to delta H m minus T m delta S m. So, at equilibrium at this melting temperature, this will be the equation, and if this is equal to 0, then we can write down this T m delta S m is equal to delta H m. We can write like this, okay. And what we can do, we can write down this delta S m is equal to delta H m by T m. So, we can get the value of delta S m, and if we place this delta S m in this equation 1, so we can write down this as a So, this I changed the color. So, basically we can write down RT ln x diopside in liquid divided by x diopside in solid is equal to. So, basically we are putting this HM term here, this SM term in terms of HM and TM. So, this will be equal to minus delta HM minus T, and this your delta SM is delta HM by TM, delta HM by TM. Okay. So, now if we take your HM outside this bracket, so what will happen? We can take delta HM outside this bracket and we can put this RT at the denominator. So, we can write down ln x diopside liquid divided by x diopside solid is equal to, because we take HM outside this and minus sign will be go inside the bracket. So, this will be your T by Tm minus 1. I hope up to this point everything is clear. Okay. Now, if we put a T inside this, so your delta Hm by R, we basically put T inside this bracket. So, this T will be cancelled by this T. So, you will have a 1 by Tm minus 1 by T. Okay. So, this is your equation. So, your final equation will be x diopside in liquid divided by x diopside in solid. Okay. So, if you see this equation, okay, if you see this equation, so this equation is called as a cryoscopic equation. This equation is called as a cryoscopic equation. This is also known as a depression of freezing point or melting point. So, this is also known as depression of freezing or melting point. Okay. So, this equation is basically suggest that when we mix a two solid, so basically if these two solids are not miscible, so we basically your melting temperature will decrease, and we will try to understand why it is called a depression of melting point or freezing point. So, suppose we have this equation, and in this equation there are different parts. So, you should try to understand that this your x DIL is a mole fraction of diopside in liquid. Okay. This x DIS is mole fraction of diopside in solid. Okay. And delta Hm is a change in enthalpy at melting point. Okay. R is your gas constant, Tm is a temperature of melting, and T is another temperature which is a equilibrium temperature of your impure phase. Okay. We will try to understand this. So, suppose we take a first case, okay, and in the first case let us take a, so there are two different situation can arise if you understand this case, if you understand this equation, if you can read this equation. First is that maybe you have a mole fraction of diopside in solid is in a pure phase. So, when you have this situation, so in that situation your this solid will be equal to 1. So, this is your first situation. When you have this situation, So, this term will be 1. Okay. So, when you have this situation, this term will be 1. So, it means that your ln x DIL will be equal to delta H m by R 1 by T m minus 1 by T. Okay. So, one by T. Okay. When you have a pure diopside phase. Okay. We do not know that the diopside which is going to the liquid will be impure or pure, but we will try to understand this, but our diopside is pure phase. Okay. So, in this situation if we see, so basically if we have suppose we can also write down this equation delta H m by R, if we take a T minus T m divided by T multiplied by T m. Okay. So, we can rewrite this equation like this. We just put a T at the numerator and T m in the other side and denominator T multiplied by T m. Okay. So, when our temperature means T melting temperature of a pure phase is equal to the equilibrium temperature of your impure phase. So, if we have a situation, suppose T is equal to T m. If we have this situation, so our this term will be 0. Okay. When this term will be 0, this whole term will be 0, and when this whole term will be 0, then our ln x diopside in liquid will be 0. Okay. And we can rewrite x diopside in liquid will be e to the power 0, that is equal to 1. So, it means that when we have a pure diopside phase, solid phase, okay, and when the temperature of melting is equal to the temperature of equilibrium of a impure phase, then all the diopside which we will get all the diopside in the liquid will be equal to also 1. So, in this situation your x diopside liquid will be 1 when you have a diopside as a pure phase and your T m is equal to T. Okay. So, in that condition you will have this kind of scenario. Okay. Let us take another example. So, we take a second example, and in the second example, suppose if we have this x diopside in liquid, that should be less than 1. Okay. Because this is the mole fraction of diopside in liquid. So, the mole fraction is varying from 0 to 1. Okay. So, we can either take 1 or less than 1. So, suppose we have a x diopside in liquid is less than 1. So, we can write down this equation. We can write down this equation ln x diopside in liquid will be your delta H m by R and 1 by T m minus 1 by T. Okay. So, if you have a x DIL is less than 1, okay, so it means that your this term will be negative, okay, because ln is less than 1 will be negative. Okay. So, if your this term is negative, okay, and if you see the delta H m by R both are positive term, so your this term will be always positive, this term will be always positive. Okay. So, if this term is always positive and your left hand side of the equation is negative, it means that this term should be negative. Clear? So, this term should be negative. How we can get this term negative? When we have 1 by T, that should be negative. Okay. So, if this term is negative or if this one is negative, in that case we will have a negative value. Okay. And how we can get this term negative? When we have a very small number of temperature, when the temperature is very, very small. So, it means that your T should be always less than Tm. Okay. When your T is always less than Tm, in that case you will have this mole fraction of diopside in liquid will be always less than 1. What does it mean? So, the X diopside is liquid is more than 1, it means that in the mole fraction of diopside which is going in the liquid, it will be only 1 when you are mixing with something else. Okay. Then only you will have this mole fraction of diopside in liquid is less than 1. So, basically you are adding impurity in the liquid. Okay. So, basically in the first situation, when your X diopside in solid is equal to 1 and X diopside in liquid is less than 1 and T is always less than Tm. Okay. So, basically because of that, this cryoscopic equation is called as a depression of a freezing point, because your T is always less than Tm. Okay. To understand this, what you should do, you should see this graph where your composition is basically plotted. Here you have a X diopside in liquid. So, this point the proportion of diopside in liquid is 0, and at this point in the left hand side you have a diopside which is going to the liquid is 1. So, basically at this point you get a melting point because it is equal to the diopside in solid. So, at this point you get a melting point of diopside, and that is close to your 1392 degree C. Okay. When you add a impurity in the system, okay, when you add a impurity in the system, so what will happen, that you add a impurity in the system. So, when you add a impurity in the system, what happens, there is a depression in temperature. So, the temperature, when you add a impurity, your melting temperature will drop. For example, if you are adding for example 30% of impurity, so your temperature drops to this one. So, when you add this 30% of impurity 0.3 x this impurity in the system, so this will be your T. When you add more impurity, the melting temperature will drop to lower temperature. Okay. So, basically in this equation, in this cryoscopic equation, the Tm is the temperature of the pure phase and T is the temperature, equilibrium temperature of the impure phase. Okay. So, because of that there is a depression in the melting temperature. Okay. To understand this system very well, what we should do, we should try to understand the diopside and anorthite system. Okay. Because this diopside and anorthite is a pure phase and they are not miscible when they are in a solid form, but their liquids are in a miscible form. Okay. So, to understand this cryoscopic equation with a case first where your solid is a pure phase, but your liquid is a miscible phase. Okay. So, your two solids are mixed together in the liquid and make a solid solution of the liquid. Okay. So, to understand this, we will try to study the diopside and anorthite system. The formula of diopside is CaMg Si2O6 and anorthite is CaAl Si2O8. Okay. This is your clinopyroxene and this is your plagioclase feldspar. So, before we start to understand this phase diagram, you should try to understand why this phase diagram is important. Okay. This phase diagram was studied by Bowen. He was a godfather of experimental petrology. He started experimental petrology in geophysical lab in Washington DC in US. And why he studied this system? Because he saw that in many different places there is a volcanic rock which is erupting at different places, for example in Hawaii. So he thought let's study some rock which is directly coming out from the interior of the earth. Okay. So we know that we have a basalt, okay, and we know that the plutonic equivalent of basalt is gabbro. And we know that gabbro is mostly made up of 50% of clinopyroxene plus 50% of plagioclase. Okay. If you see the clinopyroxene, if you analyze the composition of clinopyroxene, so it has a 3 different component. Okay. It has a 3 different component. So if you see the clinopyroxene, so the clinopyroxene is mostly a augite, and augite has a 3 different component. Okay. The first component in augite is basically your diopside. The formula is CaMgSi2O6. The second component is your Heidelbergite, and formula is CaFeSi2O6, and the third component, which is a calcium Schermak's pyroxene. Okay. So it has a 3 different compositions, three different component. So because in the gabbro we have a clinopyroxene, and clinopyroxene is mostly augite, and augite has a 3 different component, certain proportion of diopside, certain proportion of Heidelbergite, and certain proportion of calcium Schermak's pyroxene. So when you see the calcium Schermak's pyroxene, the pure calcium Schermak pyroxene is absent in nature. Okay. So he cancel out this phase, this component from the augite. Then he started to think about the Heidelbergite, and Heidelbergite has lots of iron. And when you have a iron, and when you take a iron, and when you try to do an experiment in a high temperature furnace, okay, most of these phase diagrams are constructed at 1 atmosphere at high temperature. Okay. So at room pressure and high temperature. When you put iron in a high temperature, so iron always changes its oxidation state, and it becomes an oxidized form of iron, Fe3 plus. So which creates a lots of problem. So he tried to ignore this complexities in his experiment. So he decided that let's take a diopside, and also there are a very large amount of diopside component is present, or proportion is present in augite. So he took a one end member, that is a diopside. Okay. Then what he did, he tried to saw the plagioclase. So when you see the plagioclase, so plagioclase we have a albite and we have a anorthite. Okay. And if you see the gabbro, in gabbro we mostly have a labradorite. What is labradorite? Labradorite is basically a when the plagioclase feldspar is between anorthite 50 to 70, then the plagioclase feldspar is called as a labradorite. So, because in the gabbro you have a anorthite component is relatively high compared to albite. So, he took a anorthite, okay, and because of that he took a diapside anorthite system to understand the basaltic system. So, he took a diapside at one end and anorthite at another end, okay, and we know that diapside melts at 1392 degrees Celsius. So, your this axis is your temperature in degree C, and this y axis is your basically a composition in weight percent. Okay. So, when you come from right hand side to left hand side, your diapside proportion is increasing. So, here for example, you have a 25% of diapside, here you have a 50% of diapside, here you have a 75% of diapside, and here you have a 100% of diapside. Similarly, when you go from left to right, your anorthite proportion is increasing. Here you have a 0% of anorthite, here at this point you have a 25% of anorthite, at this point you have a 50% of anorthite, and at this point you have a 75% of anorthite. So, anorthite, pure anorthite melts at 1557 degree C. Okay. So, basically when you mix a diapside and anorthite at any proportion, okay, so because of the cryoscopic equation, the melting temperature of the phase will decrease, okay, and your graph will look like this. Okay. Your graph will look like this, okay. Something like this. Okay. So, if you try to define these different curves in this particular binary system, so this line, this curve is basically this curve is your liquidus curve. Okay. So, this curve is called as a liquidus curve. Okay. So, above this curve, what will happen, that you will have only a liquid. Okay. There will be no solid above this curve. Okay. This side of the curve, just below this curve. So, in this side your diapside plus liquid will coexist, and this side your anorthite plus liquid will coexist. Okay. So, this side of the right hand side of the point, suppose this is your point E, which is a eutectic temperature, right hand side of this side above the solidus. So, this is your solidus, this is your solidus. Okay. So, this is your solidus. Okay. And below that you will have a diapside plus anorthite. Okay. And you will have two separate phases which are not miscible. Okay. So, you have a pure solid diapside phase and pure solid anorthite phase below the solidus. Okay. And at eutectic, if you write down the composition at this point, so your diapside is 58% and anorthite is 42% at this, and temperature at this point is close to 1274 degree C. Okay. So, this field is called as a primary phase field. This field is called as a primary phase field of anorthite, and this field is known as a primary phase field of diopside. Okay. At point E, that is the only point in this eutectic phase diagram where your liquid will coexist with diopside solid plus your anorthite solid. Okay. So, E is the only point in this phase diagram where you have a maximum number of phases. Okay. We will try to understand this in more detail. Okay. So, this is your phase diagram. Okay. Suppose we want to understand how the crystallization will take place in this phase diagram. Okay. If we want to understand how the crystallization will take place in this phase diagram. Okay. So, let us say we take a liquid composition of L0, okay, and this L0 has, if we draw one vertical line, okay, if we draw a vertical line, okay. So, this vertical line, along this vertical line, your composition is always fixed. Okay. So, when your composition is always fixed in along the line, this is known as a isopleth. This is known as a isopleth. Okay. So, what we will do, first we will try to understand what is the composition of L0. So, if you want to understand the composition of L0, what you should try to do, you should try to draw a line, one horizontal line, okay, one horizontal line, and in this horizontal line, this part is basically your diopside proportion. Okay. So, this is your x diopside, okay, and this part is your x anorthite. Okay. So, if you try to understand what is the composition of this L0, the liquid or the melt, which has a point here. So, the composition is basically, you have, if you see the diopside proportion in this liquid, that is 75%, and if you see your anorthite proportion, so that is your 25%. Just remember that in this L0 is a liquid phase or it is a melt phase, okay, and in this melt phase you have a single phase, okay, and in this single phase you have a 75% of diopside component and 25% of your anorthite component. Okay. It is not that you have a solid diopside proportion in 75% and 75% is remaining 25% is your anorthite. It is a single liquid phase in which you have a 75% of your diopside component and you have a 25% of your anorthite component. Okay. So, it is like a solid solution of liquid. Okay. So, when we try to decrease the temperature, what will happen, that when you try to decrease the temperature and when your magma is started to move upward and it will decrease the temperature. So, when you reach at the liquidus curve, so it will intersect at this point. Okay. When it will intersect at this point, okay, so if you draw another horizontal line and you say this point as a T1, so it is close to say 1340 or something. Okay. So, at this point, when it will intersect the liquidus curve, okay, first embryo of a crystal diopside solid diopside will crystallize. Okay. So, at this point from the liquid there will be some solid diopside will extract, okay, or precipitate. Okay. And the composition of the solid or your solid will have a S1 composition. Okay. So, at this point you have a liquid composition is L1 and solid composition is your S1. Okay. When you further decrease the temperature, okay, when you further decrease the temperature and suppose you reach at this temperature and this temperature is, say, you have a T2 temperature. For example, say it is a 1300, close to 1300. So, when you decrease the temperature, okay, and when you decrease the temperature, your melt is extracting or precipitating more solid, okay, and solid will have a S2 composition. Okay. When S2 composition is removing from the melt, so what will happen that your basically when you go from L1 to this is suppose L2 point, okay, when you are moving from L1 to L2, so basically what happens, your liquid composition is moving in this direction because you are removing a solid from the S1 from the liquid L1. Okay. At the same time you are also decreasing the temperature, which is because you are doing a equilibrium crystallization. So, basically your solid and liquid is always in contact, okay. They are not separating, they are always their physical contact, there is always a physical contact. So, basically when you have this kind of situation, your liquid is moving along the liquidus, okay. So, your liquid is moving along the liquidus, okay. So, similarly you reach at L2. When you reach at L2, so now there are two things. When you go from L1 to L2, your solid become a S1 and liquid become a L1. When you reach at T2 temperature, your liquid composition changes to L2 and solid composition changes to L2, S2. So, if you try to see that how your liquid composition changes from when it moves from temperature T1 to T2, your L1 is basically changes to L2. So, if you see L1 has almost, if you see the composition of L1, if you see the composition of L1, so L1 composition is close to your the original melt composition, that is a diopside 75 and anorthite 25, okay, anorthite 25. Okay. When you reach at L2, so the composition changes to more anorthite rich and poorer in diopside. So, if you draw another vertical line, so your L2 composition you have almost a diopside 60 and anorthite 40. Okay. So, basically your composition, initial composition of liquid changes to 75% diopside to now 60% of diopside and 40% of your anorthite when you move from this L0 to L2. Okay. So, this is a L0 composition and your L1 is also the same composition and here L2 composition. Okay. Now, the second question is that what would be the composition of S2, okay, if you compare with S1, because if you compare with L1 to L2, their chemical composition is changing. But if I ask you that what would be the composition of S1 and S2, is these two composition, solid composition will be same or different. So, if you see the SS and S1 and S2, both will have a pure diopside composition. Okay. So, if you see the S1 and S2, both have a diopside, pure diopside composition, their composition is pure diopside, pure diopside. But if you see the proportion of solid, okay, the proportion of solid, so you can determine this by using a lever rule. Okay. So, basically at this point your number of phase, and you can you can also calculate the degree of freedom and some variance in this phase diagram. So, let us start with the L0, I forgot to tell this. So, if you have at this point L0, because at this point you have only a one phase is present. So, basically you have a liquid phase. So, from the phase rule we know that P plus F is equal to C plus 2, because this is a 1 atmospheric pressure phase diagram. So, your this Gibbs phase rule, this is known as a Gibbs phase rule. So, this will change to P plus F is equal to C plus 1. Okay. So, at L0 your number of phase is 1, we do not know what is the value of F. There are two component, you have a diopside and anode side. So, you have a 2 component plus 1. So, your F at isobaric condition will be 2. So, at this one, this will be your isobaric condition and this one will be divariant field. So, your liquid can have a any this at any temperature and composition they can vary. Okay. So, temperature and composition can vary. Okay. Similarly, you can calculate the at this point at L1, your L1 you have a 2 phases. So, at L1 you have a number of phase is 2. So, your 2 plus F will be 2 plus 1. So, F will be your 1. So, your F will be 1 and this will be your univariate, and this point is called as a univariant curve, where your F is equal to 1, here F is equal to 0. Okay. So, when you reach at temperature T2, okay, when you reach at temperature T2, so suppose you have this proportion of liquid, m proportion of liquid and this proportion of your solid is producing, and this is suppose L0 because the original composition is L0. So, if we so, at T2 what will happen, that your S2 L0 is m, okay, and your L2 L0 is equal to n. So, if you want to calculate the proportion of your solid, okay, so your proportion of solid or fraction of solid, proportion of solid, so that will be equal to this n divided by total length, that is a L2 S2, that is m plus n. And if you want to calculate the proportion of liquid, okay, that will be equal to your m divided by m plus n. Okay. So, basically when you move from T1 to T2, from higher temperature to lower temperature, what is happening, that you are increasing the proportion of solid, which is a n. Okay. When you go in opposite direction, when you go to the higher temperature, what will happen, when you reach at the T1, you have a almost like a 0% of solid, or you have a just a 1 grain of solid. So, basically your this n is close to 0. Okay. So, proportion of solid will be almost 0, okay, and your liquid will be almost 100%. Okay. So, basically when you are decreasing the temperature, your proportion of liquid is always same. Here your proportion is m, that is the proportion of liquid. Here also the proportion of liquid is m, but because you are increasing the proportion of solid, because of that your reaction is producing more this proportion of solid. Okay. You are keeping the proportion of liquid same in this decrease in temperature when you are decreasing the temperature. So, you basically your this solid composition S1 to S2 both are pure dioxide, but from the difference from S1 to S2 is that your composition, your proportion of the dioxide is varying. So, you are basically producing a more this dioxide when you go to the lower temperature, and your melt is also progressively becoming more enriched in anorthite. So, this reaction will continue until you reach at a eutectic point. Okay. When you reach at eutectic point, what will happen that when you reach at eutectic point, so at eutectic point your composition will be close to your at eutectic point your composition will be close to dioxide 58 and anorthite 42. Okay. Your composition will close to 58 and anorthite 42. Okay. Once you reach at this point, at eutectic point, and suppose your liquid is L3 and your solid is your S3. Okay. You just started to reach at eutectic temperature, where you still have a dioxide crystals. Okay. You have not started to produce a anorthite now, but at S3 you have you basically have dioxide, but if you see your proportion of your N is even more when you come from this T2 to, for example, this one is your T3, which is equivalent to 1274 degrees C. So, at T3 you have a L3 and L3 is coexisting with S3, and at this point you are not have any anorthite, you just have a dioxide. But when you give more heat to the system, okay, what will happen that because at this point your eutectic composition, yet at eutectic point your liquid composition will always coexist with your dioxide and anorthite crystal. Okay. Your this liquid composition, eutectic liquid composition will always coexist with your dioxide and anorthite crystal. So, at T3 you have you will have your liquid composition 3 that will coexist with your dioxide solid and anorthite solid. Okay. So, you will have a impure this liquid 3 composition, which is richer in anorthite composition compared to T2 temperature, and then you have a solid dioxide pure phase and solid anorthite pure phase. So, once your liquid will precipitate anorthite, what will happen that your composition will move in this direction, and then you will have a S4 composition, and at this S4 composition your liquid will have a L4 composition. Okay. And this S4 composition you will started to precipitate your anorthite crystal, because the composition of L3 and L4 is exactly the same, because even though you are supplying a heat to the system, heat is basically in the form of latent heat of fusion. So, you basically decreasing the melt proportion, okay, but your composition of the melt will be always same. Okay. So, L3 and L4 both will have a eutectic composition, and in this eutectic composition you have a 54% of dioxide component and 42% of your anorthite component. So, when you try to precipitate anorthite from that melt. Okay. So, the proportion of diopside and anorthite will be, the proportion will be the same as depending on the proportion of component of diopside and anorthite in the liquid. Okay. So, when you reach at S4, you started to precipitate anorthite, and you can basically calculate the proportion of your diopside and anorthite in this particular S4. Okay. So, the main difference from S3 to S4 is that at S3 your eutectic liquid L3 will coexist with your diopside, but once your liquid, when you decrease the temperature, your liquid will started to precipitate anorthite, and once anorthite is started to precipitate from the liquid of the eutectic composition, your solid composition will move along this eutectic horizontal temperature, this horizontal line, and move towards this, because your eutectic composition is at this point. So, only at this point you have a liquid which is coexisting with diopside and anorthite. So, basically at S4 you will have a diopside plus anorthite plus liquid, and if your original composition is this one, and if you draw like this, okay, so you have a L0 is here, this is your S4 and this is your L4. So, this will be your proportion of liquid, and this will be your proportion of your solid, and you can calculate the proportion of liquid and solid, and you can also calculate in this proportion how much diopside is there and how much your anorthite is there. If you draw a vertical line, so basically in this particular S4 point you have a 90% of diopside and 10% of your anorthite. So, basically from this we can easily calculate this diopside and anorthite proportion, and also the proportion of the liquid. If we further decrease the temperature, so when will be the last drop of the liquid will coexist? When your S4 will move to this point, when your S5 composition will be exactly at the L0 composition, and in this L0 composition what will happen, that your basically your this liquid composition will completely exhausted, and you will have only this diopside and anorthite. So, at this point when your last drop of liquid will be exhausted, when your M will be equal to 0, and M will be equal to 0 when your S4 will move to L0. So, that is your S5 will move exactly at the L0 point. So, at this point your proportion of liquid, that is M plus N, this is equal to 0. So, this will be equal to 0. So, at this point your liquid will be your 0. So, this will be the last point where you will have a liquid. Okay, you will have a last drop of liquid that will be exhausted. So, if you see this phase diagram, okay, so what you will observe, that this solid composition, your liquid composition is changing. So, if we we will try to sum up here, and we will try to start the next lecture from this point. Okay. So, I think I will stop my lecture here, and we will try to understand this eutectic phase diagram from this point when we have a last drop of liquid is exhausted. So, how our solid composition change and how our liquid composition change in case of your equilibrium crystallization case. Okay. We will also try to understand that in case of fractional crystallization what will happen, and we will also try to understand when we have a rock and we melt that rock, what will happen in case of equilibrium melting. Okay. So, in these 3 examples we will try to cover in the next lecture. So, I will stop here. Thank you.